actually looked at thus far. All right? For example, we looked at the linear function in which the general equation that we can write here for the linear function was of what pattern? Brenda says y is equal to mx plus b. Okay? And then let's see now, from the linear function there were a number of special cases that we considered, one of which was the constant function. And what was our general pattern for the constant function that we have had thus far? Chuck? Y is equal to a constant, which in this case, if the slope number m is 0, y is equal to, Ken?
B.
Y is equal to b. And then in fact, I think, Chuck, we had a function which we call the identity function, in which, what was the equation for the identity function? Y is equal to x. All right? And then in fact, I think we had a few other examples of functions that we've considered thus far. There was what? The absolute value function. The absolute value function in which, what was the pattern for it? What? Y is equal to, and what was our notation in which we used these two bars to indicate the absolute value function. Is that right? Okay? And then let's see now. There was another function that we looked at. In fact, it was this direct variation function that we worked on yesterday, the direct variation function. And what was the general pattern for that? And anyone? What was the pattern for the direct variation function? Remember now the y-intercept was 0, and Steve says
Y equals mx.
y is equal to m times x, what we call m that constant of proportionality. And then in fact, yesterday we took another special function that we considered, in which, if you remember, it was called the greatest integer function. All right, and there was this notation which had these square brackets that were rather heavy, and we call that the greatest integer function. All right, so these are the different examples of functions that we've looked at thus far. They're all more or less special cases of the linear function, except the absolute value and the greatest integer function. Okay, those two were not of a linear nature. And for today, what I'd like to do is to introduce another function in which it is called the quadratic, Q-U-A-D-R-A-T-I-C. And the general pattern for the quadratic function is as follows. It's y is equal to ax squared plus bx plus c, where the number a here cannot be 0. Okay? And so this is the example, this is the function that we'd like to concentrate on today. Now, let's come over to our coordinate system, and let's take a very special case of that function in which we'll have y is equal to x squared, okay? In which, notice now, the number a here is what? It is understood to be what value?
1.
The number a is 1, okay? Now, let's actually graph this function on our coordinate system, and let's just take a lot of ordered pairs, and then I think we'll see some patterns which will emerge. Now, of course, if x is 0, what number must y be? 0. And right here then is the point 0, 0 right at the origin. Is that right? Now if x is 1, y is what? 1. If x is negative 1, y is 1. If x is 2, y is what? What? 4. 1, 2, 3, 4. Is that right? If x is negative 2, y is 4. Is that right? Okay. If x is 3, y must be 9. That's 4, 5, 6, 7, 8, 9. All right. If x is negative 3, y must be 9. Is that right? If x is, say, 4, y must be 16. There's 9, 10, 11, 12, 13, 14, 15, 16. All right? And in fact, if x is negative 4, 2, 3, 4, y must be what? 16. Now, notice for the first time we see another kind of a curve in this case, in which if we were to consider the domain for x, all right, to be the set of all real numbers, I think you will agree that we can have here a nice smooth curve in which it will pass through these points, all right, passing through these points, in which it's going to come to a nice smooth curve down through the origin here, all right, in which it then will continue on forever in this direction, okay? And this curve is a special case of this quadratic function in which the number a here happens to be 1, okay? So if I were to write this situation, which we have y is equal to ax squared, notice a happens to be what? It's positive, in which I can indicate this in this fashion. And notice In the case in which A is positive, we have the curve opening upward. Is that right? It opens upward. Is there any place here about which one sees an axis of symmetry? Is there any symmetry here? Is there a line through which there is some symmetry in which, for example, if I come out x is 1, we have 1 comma 1, there's also the point negative 1 comma 1. If x is 2 comma 4, there's also the point negative 2 comma 4. So there's some line about which we have symmetry here. Ron says the y-axis. In fact, what's the equation for that y-axis? What is our equation for the y-axis? What do we say about the equation for the y-axis, Steve? X is equal to 0, okay? Let me call this the axis of symmetry in this case, all right? The axis of symmetry, in which in the case that we have here, it happens to be the y-axis in which its equation is x is equal to 0, okay? We call this point down here, it's given a special name in which it happens to be at the origin in this case, all right? We call this the vertex point, all right? The vertex point. And now notice, because our curve opens upward, do we have there a maximum or a minimum? And what do you think? Well, with respect to our curve here, is it a max or a min? And everyone says, well, that's the minimum value that the curve can take on. Is that right? So we think of this as a minimum point. Okay? Now, let's come over and look at a second example. And notice in this picture, I happen to have y equals x squared already graphed on this coordinate system in which it is a dotted line. And the reason I wanted to do that was to compare it with another curve such as y is equal to 2x squared. Now let's take this value of a to be 2, okay? And again, of course, the number 2 is positive, so we suspect that the graph is going to continue in a pattern such as this. Well, let's take some ordered pairs here and see what happens. Suppose x is 0, okay? And again, I think you'll agree that y has to be 0. Now, if x is 1, y has to be what? 2. 1 squared is 1, and 2 times 1 is 2, so it will be this point. Notice it happens to be inside of the dotted curve. If x is negative 1, y is 2, okay, which is this point. If x is 2, y is 8, all right? So there's 1, 2, 3, 4, 5, 6, 7, 8 is this point. If x is negative 2, y must be 8, which is this point right here. Is that right? If x is 3, y must be 18. Is that right? So there's 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 right here. And of course, if x is negative 3, y must be 18. Now, let's try to make a curve which is going to pass through those points. In this case, I'll make it a solid line in which it's going to pass through those points. Notice it's a rather tall and narrow curve. Is that right? In relation to x squared. Now notice that number 2, all right, let me put arrowheads indicating that it goes on forever. Now notice in this case the curve is inside of the dotted curve. And the number 2 has a tendency to make the curve, what? Long and narrow, so to speak. Is that right? It's going to be inside of the curve of x squared. Okay? Now suppose we have the curve y equals 3x squared. Where do you think the 3, what effect is the number 3 going to have on this curve? Is it going to make it what? What? More narrow. Is that right? Now how about, suppose we had a number such as y equals 1/2 x squared. What do you think the effect of that number 1/2 is going to be with respect to the dotted line, Ron? It will open up. That is, it's going to what? You think that it's going to be more on the outside of the dotted line. Is that right? Suppose we had y equals 1/4 x squared. Where do you think that would be? Would it be even a bit more open? Is that right? Okay? In a pattern such as that. So let me indicate this curve to be the case of y is equal to 2x squared. Okay? Again, notice our axis of symmetry is where? What is our axis of symmetry? It's the y-axis. All right? We give a special name, by the way, to these curves in which it is called a what? A parabola. Okay? We call this curve a parabola. All of these are in a parabolic shape. Every one of them now. They're all either going to be narrow or wider in relation to, say, y is equal to x squared. Okay? Let's now look at a third example. And notice in this picture, I happen to have the curve y is equal to 1/4 x squared given to us as a dotted line. All right? And what I'd like to now consider would be a curve such as y is equal to negative 1/4 x squared. Negative 1/4 x squared. And let's see what the effect of this dash symbol has on this picture, okay? Well, let's see what we can say. If x is 0, of course y must be what? 0, so this point is still on this new curve, is that right? Now, if x is 1, 1 squared is 1, and negative a fourth times 1 is negative a fourth, so it must be on this side. If x is negative 1, y must be what? Is negative a fourth, is that right? Suppose x is 2. 2 squared is 4, and negative the fourth times 4 is negative 1. So this point now must be on the curve. If x is negative 2, y must be negative 1. If x is, say, 3, is that right? Or in fact, let's take a number 4. If x is 4, 4 squared is 16, and negative a fourth times 16 is negative 4. So we come out here, what? 1, 2, 3, 4, and we're coming down 1, 2, 3, 4. Is that right? So this point must be on the curve. And of course, if x is negative 4, 1, 2, 3, 4, y must be what number? Negative 4. All right? So this point must be on the curve. Let's go out, say, to 6. 1, 2, 3, 4, 5, 6. If x is 6, 6 squared is 36. Negative a fourth times 36 is negative 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And this point must be on the curve. And I think you will agree that the corresponding point, because of symmetry, which is this point here, will also be on our curve. So now let me try to draw this with a solid line in which we are going to have a curve coming in this direction, in which, notice, it opens downward, okay? It opens downward. And here is the graph of y is equal to negative 1/4 x squared. So what is the effect of the dash symbol on, say, y is equal to ax squared? In this case, we happen to have the number a, which is negative. So what then affects the graph when this number a is negative? What do you think happens? Can anyone come to any conclusion, Chuck?
That it will be on the opposite side of the x-axis, and 0 will be the maximum.
All right. In this case, now we're going to have a maximum, and in fact, the curve is going to, if you think of this in terms of flipping it over the x-axis, it's going to be what we may think of as opening downward. Is that right? And so anytime we have the number a, which is a negative number, the curve, which is still a parabola, is going to open downward. And of course, if it opens downward, our vertex point then is going to be a maximum. Our axis of symmetry is still in this position here. Okay? Let's look at a fourth example. In this case, we have y is equal to x squared minus 4x. Now notice, on the other examples, we had simply y is equal to a times x squared. Now I have something of the pattern ax squared plus bx. All right, now what is the number b? What value does b have in this case? Negative 4, okay? Now, let's see how we can look at this. Suppose I set it equal to, and let's factor out that number x and think of it as x times x minus 4, okay? Now, y is our ordinate value. That's the height above the x-axis. And when y is 0, is that right? When y is 0, what then can we say about x? What numbers will x have? X will be 0, which is, that's going to then be 0, 0, which is at the origin. And how about, is there another value for x which will make y 0? When x is what? 4. 1, 2, 3, 4. Now, our graph is going to pass through. It's going to be a parabola somewhere, and it's going to pass through those 2 points. Is our parabola going to open upward, or is it going to open downward? And you can look at the number a. In this case, the number a is what? Is 1, so it's going to do what? Open upward, okay? Now, where is the axis of symmetry going to be? As we draw this graph, we don't know exactly where it is yet, but it's going to be somewhere in this position. Where must the axis of symmetry be going to be? And Brenda? At x is equal to 2, right in the middle here between the 2 points at the origin of 0, 0 and at 4, 0, okay? So right there, at x is equal to 2, let me draw, in this case, a dotted line, which is going to be our axis of symmetry, okay? And I think then from that, it's going to help us make our graph. Let me indicate this with an arrowhead, in which there you'll have what? The axis of symmetry is what? Y, or what do we have there? Not y, but what? X is equal to, in this case, 2, okay? Now, when x is 2, y is going to have its what? It's max or it's min. When x is equal to 2, I think you all said that we're going to have a curve which is going to open upward, therefore we're going to have a minimum. So let's find out where that minimum value is. So what then can we let x be? Let's let x be 2. So let's substitute 2 in here. 2 minus 4 is what? Negative 2 times 2 is negative 4. So when x is 2, we're down here 1, 2, 3, 4. And this point must be on our curve, okay? Now, let's take a value, say, of x is negative 1 and find a third point. And if x is negative 1, we have here negative 1 minus 4 is what? Negative 5 times the negative 1 is positive 5. So we're up there 1, 2, 3, 4, 5. This point must be on our graph. Notice because of our symmetry, we can come over here 3 units in order to get that point. So we must come on this side 3 units. 1, 2, 3 units. And that's going to give us a point on our curve. In fact, let's take another point if x is negative 2. And if x is negative 2, we have negative 6 times negative 2 is 12. So if x is negative 2, we're up at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This point must be on our graph. And in fact, a corresponding point, because of the symmetry, 1, 2, 3, 4. We can come over here, 1, 2, 3, 4. And this point must be on our graph, okay? Now again, through those points, we can draw a nice smooth curve in which the picture is going to look something like this, passing through these points. And it's going to have a nice turning point down there at the vertex, and our graph is going to look like this, okay, in which we then will put arrowheads on. Now, where the graph crosses the x-axis are given a special name, in which these points here are referred to as the, well, we may think of them in terms of the zeros of the function, okay? The zeros of the function. If you go back here and think about the function itself, where y is 0 is where the graph crosses the x-axis. Is that right? So we speak of those as the zeros of the function. By the way, if we had to put in the coordinates of this minimum point here, what are the coordinates? What then may we write here as our coordinates? We come out here what? 2 units and what? 2 comma negative 4 would be the coordinate. Now, is this going to be a maximum or a minimum point? It's a minimum. Okay. Let's look at another example in which we have here y is equal to a negative 2x squared plus 8x. Now, again, let me rewrite this equation in a somewhat different pattern, this formula, in which let's now take out a number negative 2x. And if we take out a negative 2x, what's left? But we have what? X, what? What? Minus, what? X minus 4. Is that right? Now, again, what are the zeros of the function? What are the zeros of the function? When y is equal to 0, that's where our graph is going to cross the x-axis. So what are the zeros of the function? One of them occurs here. That we have one at 0, which is going to be x is 0, y is 0 at the origin. And the other one is where? When x is 4. 1, 2, 3, 4. And in fact, these are the same 2 points we had in the other graph. Is that right? Okay. Now, because of this number a, what is the value of a, by the way? Negative 2. And because a is negative, is our parabola going to open downward or is it going to open upward? Downward. It's going to open downward, okay? Now, because it's going to open downward, this is our parabola. Where is the axis of symmetry going to be? Where is the axis of symmetry? What's the equation of the axis of symmetry? We have this point here and this point here, which must be on the curve. These are our zeros of the function. And where must the axis of symmetry be? Ken?
X equals 2.
X is equal to 2, which we can indicate by this dotted line. Okay? Let's include it right in here and see what we can say. Now, if x is equal to 2 is our axis of symmetry. Now, when x is 2, we're going to have what? Our maximum or our minimum point? When x is 2, we're going to have a max or a min. That's our maximum. So let's substitute x is 2 in here and find out what that value for y is. And if x is 2, 2 minus 4 is negative 2. A negative 2 times 2 is negative 4 times a negative 2 is 8. So when x is 2, we must be up at 8. 1, 2, 3, 4, 5, 6, 7, 8. And this point must be on our graph. In fact, let's include that ordered pair of 2 comma 8 as our what? Our vertex point, which is a maximum. let's take another value for x. Oh, let's say that x is, say, -1. And here if we substitute x as -1 minus 4 is what? -5. -2 times a -1 is 2 times a -5 is -10. So here when x is -1, we're down at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This point must be on our graph. And if this point's on the graph, because of the symmetry, we can come over 1, 2, 3 units. So 1, 2, 3 units. This point must be on our graph. And notice our graph is rather tall and narrow because of what number? Because of what number? Because of the number 2. And in fact, it is going to be opening downward because of what? Because it is negative. Okay? Let's look at a sixth example and see what we can say about this. Notice in this situation we have here x squared minus 4x plus 4. And for the first time now we have a value of a which is what? 1. B is -4, and now we have a value of c which is 4. So let's see what we can say in this situation. Let me rewrite this in a slightly different pattern. And notice here we have x minus 2, the quantity squared. Is that right? Now, remember, any number squared is always what? Is always positive, or certainly what? Non-negative. So the smallest value that y can possibly have is what? Is 0. All right? Well, what number x is going to make y 0? 2. Okay? So right at 1, 2, this is going to be what? Because the number a here happens to be 1, is our graph going to open upward, or is it going to open downward? It's going to open upward. Now, this point is going to be what? A max or a min? A minimum. So let's put in the coordinates of that point right now, which is what? 2, 0. And in fact, is that going to be our axis of symmetry? Is our axis of symmetry going to be right there? Is that right? Okay, so let's include a dotted line there for our axis of symmetry. All right, which is going to be this line, x is equal to 2. All right, let's include that as our axis of symmetry, which is x is equal to 2. Now, let's take some points. Well, perhaps an easy point to take is when x is 0. An easy value to take is when x is 0, looking at this sentence, y must be equal to what number? Y must be 4. Is that right? So if x is 0, y must be 1, 2, 3, 4. This point must be on the graph. Well, if this point's on the graph because of the symmetry, this point must be on the graph. Is that right? Oh, let's come out here and say the -2. -2 minus 2 is what? -4. -4 squared is 16. I'm not sure I can get on my graph. -2, we want to come up to 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12, 13, 14, 15. 16 is right here at this point. Because of the symmetry, we've come out 1, 2, 3, 4 units, so we can come out 1, 2, 3, 4 units, and that point must be on our graph. Let me take one more point, such as when x is -1. -1 minus 2 is -3. -3 squared is 9. So we come up 1, 2, 3, 4, 5, 6, 7, 8, 9. This point must be on the graph. We come out 3 units, so 1, 2, 3 units here. This point must be on the graph, and in fact, through those points, we can draw a nice smooth curve, which is going to look like this. And then on this side, a nice smooth curve, which is going to look like this. Notice now it's going to come to a nice turning point down there, in which we then will put our arrowheads on there to indicate that it goes on forever. And here then is the graph of this function. All right? Notice, by the way, that the graph just touches the x-axis at that point. It just touches the x-axis. So the zeros, the 2 zeros that we have, really are one and the same number. Okay? Let's look at another example. And notice in this case now we have y is equal to a -x squared, the opposite of x squared, minus 2x plus 8. Now what is the value for a? -1. What's b? -2. What's c? 8. Okay? Now because a is -1, is the graph going to, is it going to open downward, or is it going to open upward? Downward. It's going to open downward. All right, let's now write this in a slightly different pattern. Notice in each case I look at it from a slightly different pattern. Let's take out the opposite of all of this. And whatever is left, we have what? X squared, is that right? Plus 2x, is that right? Minus 8. Okay? Now we look at that and we say, well, I think we can factor that into what? There's x times x is x squared, and it's what? Plus 4 and a minus 2 is going to give us a plus 2 in there. Is that right? Everyone agree? Now, again, y is equal to the opposite of x plus 4 times x minus 2. What are the zeros of the function? What are the zeros of the function? Where does the graph cross the x-axis? When x is negative 4, 2, 3, 4, and when x is 2. Is that right? When x is 2. So those 2 points must be the zeros of the function. Is it going to open downward? Everyone says it's going to open downward, so our graph's going to look like this. Where is the axis of symmetry? What's the equation of the axis of symmetry? At x is where? Right in the middle, which is negative 1. So right there, let's draw a line, which is a dotted line, which will be our axis of symmetry. Okay? And let's go on from there. Okay? Now, when x is negative 1, what then is our maximum point? Well, let's just substitute in here. Negative 1 plus 4 is 3. Negative 1 minus 2 is negative 3. And 3, a negative 3 times a negative 3 is 9. So you're up at 9. Okay? So when x is negative 1, you're up at 1, 2, 3, 4, 5, 6, 7, 8, 9. This point right here must be a vertex point. In fact, let's put in those coordinates of what? Negative 1, comma, 9. Now, let's take one more point somewhere, perhaps when x is, say, 1, 2, 3, and see what value we get. When x is 3, we have what? 3 plus 4 is 7. 3 minus 2 is 1, so you're down at, where? Negative 7. 1, 2, 3, 4, 5, 6, 7. I think that's all we need. And then on this side we come out 1, 2, 3, 4, so we can, by symmetry, come over here 4 units. And in fact, I think I can make a graph which is going to pass through those points. It's going to open downward, is that right? And it's going to be a nice smooth curve passing through those points. Notice our axis of symmetry is the line what? X is equal to what? Negative 1. And in fact, we have a maximum point, which is our vertex at negative 1, comma 9. Okay? Let's look at one last example. I think that's all that we need to do for today. Notice in this case we have y is equal to 1/4 x squared minus 2x plus 3. Now, because the number a is positive, is our graph going to open upward or downward? Upward. Now, because it's 1/4, is it going to be tall and narrow or wide and fat, so to speak? Wide and fat. Okay. Now, let's you see, you know all of that before you even start. So this gives you some idea of what to look for. Now, let me take out that number 1/4. All right, if we were to factor out a 1/4, we have left what? X squared minus. Now, 1/4 of what number is 2? Is what? Is 8. Is that right? So it's a minus 8x plus 1/4 of what number is 3? 12. All right? Now, notice I'm writing this in a different pattern in which we have 1/4 times. Now, let's hope that we can factor this. There's x times x is x squared. And here we have what? A negative 6 and a negative 2 is a positive 12, in which we end up with a negative 8 in the middle. Is that right? Okay? Now, again, what are the zeros of the function? 6 and what? 2. All right, let's come out here 2 units, and 3, 4, 5, 6 units are our 2 zeros. Our graph is going to open up. Is that right? And now, where is the axis of symmetry? What's the equation of the axis of symmetry? X is equal to 4, right in here. Is that right? So let's include that as a dotted line. X is equal to 4. All right, in which we have it right here. And let's include that. X is equal to 4 is our axis of symmetry. Now, when x is 4, let's find out what our number y must be. So 4 minus 6 is negative 2, and 4 minus 2 is 2, and what? 4, right? That's a negative 4 times 1/4 is negative 1. So this point must be on our axis of symmetry. Now, when x is 0, it's easy to go right back to the original sentence here. Y must be what number? 3. So when x is 0, y must be 1, 2, 3. This point must be on the graph. And of course, because of the symmetry, we can come over here 4 units, 1, 2, 3, 4, and that point must be on the graph. Let's take, let's say, negative 2. If x is negative 2, we have what? Negative 2 minus 6 is negative 8, and a negative 2 minus 2 is negative 4, and we have there what? 8 times 4 is 32, and a fourth of 32 is 8. So when x is negative 2, we're up at 8. 1, 2, 3, 4, 5, 6, 7, 8. And in fact, because of the symmetry, we're over here, what? 1, 2, 3, 4, 5, 6. We can come out this side 6. 1, 2, 3, 4, 5, 6. And I think that's all that we need to do in order to be able to draw a nice smooth curve through those points. Now notice, in this case, the curve is rather wide, right, and fat, in which it is spread out. And what makes it spread? What is the number? The number 1/4 has that characteristic. By the way, what then are the coordinates of our vertex point here, which happens to be a what? Is it a max or a min? It's a minimum. What then are the coordinates of this vertex point? At where? 4, negative 1. Well, I think that's all that we need to do for today. So let me give you your assignment, which has to do with some of these pictures. Please, make your graphs for this homework assignment on a coordinate axis, all right? Rather than just in your notebook, have some nice graph paper in which you can do this.